where I have this R code from our last class meeting when we went over this. I didn't mention this last time, but this conf.int equals true, that's optional. You don't have to write that line of code as part of your line of code. It's going to automatically give you the confidence interval, all right? So you can leave that off if you like in that line of code. It's not necessary. But if you look at this output, notice in the hypothesis test section of the output, it talks about odds ratios, right? So we're using the same line of code for Fisher's exact test and the odds ratio test, all right? But we were looking at the confidence interval last time, and notice our confidence interval is given here in this highlighted region, and I gave that interpretation last time. Now, when we dealt with, let's see if you guys really remember some of the stuff from the relationship between confidence intervals and hypothesis tests, right? So when we were doing, let's say, a 95% confidence interval for mu1 minus mu2, right? And we said that, oh, well, if we tested the null hypothesis that mu1 equals mu2, we can draw conclusions about this null hypothesis using the confidence interval. But we had to look at whether a certain value was within that confidence interval or not. What value did we compare? Allie? So when we were doing the confidence interval for mu1 minus mu2, right? We said that we can use the results of this confidence interval to draw conclusions on whether we're going to reject the null hypothesis or not for this hypothesis test, right? What number were we looking to see whether it was in the confidence interval or not?
0.
0, right? Because remember we said that we could write this hypothesis test this way as well. And so if 0 was in the confidence interval, it's probable that mu1 equals mu2, or mu1 minus mu2 is probably going to equal 0 if it's in the confidence interval. If it was not in the confidence interval, we would have enough evidence to reject the null hypothesis and conclude the alternative, all right? But we compared it to 1 because we did the subtraction, and we compared it to 0 because we did that subtraction, and we rewrote that null hypothesis in this form right here, right? So when we're doing our hypothesis test or our confidence interval for theta, right? Our null hypothesis every time we do the odds ratio test is that theta equals 1, right? So we can do a similar thing here, right? Instead of looking for 0 being within the bounds of that confidence interval or not, since our null hypothesis has a 1 on that other side, I can determine if 1 is in the confidence interval or not. If it is not, that is enough evidence to reject the null. If it is, I don't have enough evidence to reject the null hypothesis, right? So if I look at this confidence interval that we got here, right? It's from 1.53 to 3.43, right? Is 1 within the bounds of that confidence interval? The value 1, the number 1. No, right? It starts at 1.53 and it ends at 3.43, right? 1 is smaller than all of those values in that confidence interval. So it is probably not probable that this is going to equal 1 because it's not in my confidence interval. So when I see a confidence interval like that, I already know that I'm going to have enough evidence to reject the null hypothesis in this case right here, all right? So you can use that same principle that we applied when we did mu1 minus mu2 equals 0, or the mu d equals 0, looking at whether 0 is in the confidence interval. But this time, all we have to do is look and see whether 1 is within the bounds of that confidence interval. All right? So that stuff still applies as we go through these additional tests here. All right? But that is your confidence interval. So let's continue with the last example in this section, which is example 5. So this is a different scenario. All the others were based off of the smokers and former smokers, right? Here we have a randomized controlled trial, right? It says N equals 1,360 stroke patients were randomly assigned to receive aspirin or placebo, right? So this is an experiment here. In the last example, we had an observational study. This is an experiment. And if you've taken previous statistics courses or you talk about it in your some of your science classes or psychology, remember you can say that one thing is causing your response variable to behave a certain way when you're dealing with experiments, right? There's a cause and effect relationship between your variables. So some of the individuals are getting the placebo, others are getting aspirin, right? And we have a fixed group number of individuals who are getting the placebo and the aspirin, right? Because we're randomly assigning them. All patients were followed for about 3 years. And then the researchers were interested in whether there's an association between aspirin and having a heart attack. So they were going to record whether there's an incidence of a heart attack for each of those individuals. All right. So notice here, it didn't say anything about doing your odds ratio test, using the odds ratio test, right? It just asked, or we're focusing on, is there an association between aspirin and having a heart attack, right? Remember, the word association is related to the word relationship, right? They're synonyms. And so we could apply the chi-square test of independence in this example, right? I would see if all of my expected counts are greater than 5. And if that's the case, I can calculate my chi-square statistic, get my p-value, and then draw my conclusions there, right? But the chi-square test is basically, are your variables related or not? And that null hypothesis is P1 and P2 equals P2. But I just went over the fact that, hey, this null hypothesis here and this one, they are equivalent. And so since we're talking about the odds ratio test in this section, I'm going to apply the odds ratio test here. All right. Now, if we were doing this in real life, we would do that. But it says use RStudio to determine if the variables are related. If they are, then construct the 95% confidence interval. All right. So, yeah, I'm going to do the test for theta equals 1 here. All right. It doesn't tell me my alpha, so I'm going to, it says for me to construct a 95% confidence interval. And so I'm going to let my alpha, which is my significance level, be 0.05. That aligns with a 95% confidence interval. All right, of course, on your exams, I always state what your significance level is going to be. All right, so I've got to enter my data, and I'm going to enter it just the way I see it on this chart here. Got to enter it as a matrix, so I'm calling my data set aspirin. You can call it whatever name you want. It equals, I'm going to use my matrix function here, enter my first column and then my second column, right? And I tell it the number of rows. Now, if I'm just wanting to see if these variables are related, my alternative hypothesis is theta does not equal 1. All right, it doesn't tell me that I'm expecting one directional to do a directional test, so I'm going to assume that it's non-directional. And that's going to still tell me whether my variables are related or not, or associated. All right, so I'm going to do my Fisher.test, put my data set name into RStudio as the first piece inside the Fisher.test function. Remember, you can leave off this conf.int equals true. I believe at one point in time you needed to include this. You do not have to include that here. That is optional. And then my confidence level here is 0.95. All right. And so I see from my hypothesis test, or my results from RStudio, that my p-value is 0.1768. That is greater than my alpha. So I'm going to fail to reject my null hypothesis. All right. So in this study, based off of what I have here, there is insufficient evidence to conclude that these two variables are related. We have not gathered enough evidence to conclude that those variables are related, right? So I can write that as my conclusion, all right? But, you know, we're in, you know, the life and biological sciences, right? And so we could state this a little more specifically here in the context of this experiment, right? We're trying to see if whether taking aspirin is going to either increase or decrease your incidence of a heart attack, right? Does it have an impact on the incidence of a heart attack, right? And so we've not gathered enough evidence, so I'm going to draw my conclusion this way. There is insufficient evidence to conclude that aspirin impacts or affects an individual's incidence of a heart attack. If you were just to say that the variables are related, that is perfectly fine, right? But this is what we're really trying to get at in this study. And as you do more and more statistics and you get more and more comfortable, you want to draw conclusions that are relevant in real life and just instead of just statistical terms. All right? Now, if you notice here, the confidence interval is given here. You notice we failed to reject an null. And guess what number is within the bounds of that confidence interval? The number 1, right? So remember, it's probable that our null hypothesis is true when 1 is in our confidence interval, so we would fail to reject. All right? So now that we have all of this stuff here, right? So when we want to know whether two categorical variables are related, right? Or we want to do a comparison of studies with two categorical variables. We can use the chi-square test of independence. We can use Fisher's exact test. And we have our odds ratio test, right? When we want to compare proportions, we can do P1 minus P2, P1 divided by P2, that was your relative risk, or we could do our odds ratio. So we have a lot of choices here, right? This is a traditional statistical method here, right, when we're comparing proportions. But a lot of times, especially in medicine and healthcare, P1 and P2 are going to be small proportions. They're going to be close to 0, right? When you think about a large population, you know, think about like the incidence of getting lung cancer or breast cancer, right? I know many people develop those diseases or those cancers, but in the greater population, that's a very small proportion of individuals, right? And so in medicine, we sometimes don't like to use P1 minus P2, right? Because practically, we might not be able to see how much of a difference those proportions are, right? That's why in medicine, they prefer to use this method here and this method here, all right? Where we can compare through division. Now, we didn't focus much on the relative risk in this course. And the reason for that is because some studies, the relative risk cannot be computed. And so we'll look at some examples of that case on the next page in our notes. All right. So it says, in many applications, the odds ratio and the relative risks are approximately equal to each other. So they're not going to be identically equal, but they're going to be approximately equal to each other. And there's sort of a preference for the odds ratio, which is why we spent more time on that. The true relationship between those, if you solve the odds ratio, I'm just going to say theta, it's going to equal your risk ratio or your relative risk times 1 minus P2 over 1 minus P1. All right, so they're pretty much equal to each other. All right, but I don't like to use the risk ratio because I'm not always going to be able to calculate it. And so I'm going to go over two studies that's used in, or two study designs that's used in medicine a lot. And we'll see that sometimes if we try to apply the methods that we've used to calculate P1 and P2 or P1 hat and P2 hat, sometimes I shouldn't apply that method. One of the types of study designs is known as a cohort study. And in a cohort study, you're going to start with a group of subjects who have a defined characteristic. And then you're going to follow them over time to see if they develop an outcome of interest. And I know we've used that lung cancer example before, so I'm going to go back to that example. But I'm going to redesign the study to fit a cohort study. Remember in that other study, I just had one large sample of 11,900 individuals. And I just basically looked at their health histories to see if they were former smokers or smokers, and then whether they developed lung cancer. Well, in a cohort study, we're going to find, let's say, a random sample of 500 smokers, and then we're going to have a random sample of 500 former smokers. So I'm going to choose those at the onset or at the beginning of the study. Then I'm going to follow those people over several years, kind of like in that last example. And let's determine whether they develop lung cancer or not. So in this type of study, at the onset, we have our cohorts of individuals, right? 500 smokers, 500 folks who stopped smoking. That was fixed or predetermined. And so if we were going to see if these two variables were related, right? Does smoking, being a smoker versus a former smoker, impact your incidence of a lung cancer? Then I can go through my chi-square test or my odds ratio test. I can calculate P1 hat and P2 hat in the normal way that we would calculate them, right? P1 hat will be 7 over 500. P2 hat would be 3 over 500. There's no issues here. I can use the chi-square test of independence. I can use a relative risk, and I can use my odds ratio, right? These both can be calculated, all right? So there's nothing new here. If I have a cohort study, I can do what I've been doing, all right? But when I have a case control study, which is a type of study that's used a lot in medicine, I'm going to run into some issues, all right? So in this case control study here, we're going to start by identifying people with the outcome of interest first. So notice in this study, I know that smoking is related to lung cancer, right? So I'm going to fix or predetermine a sample of smokers and former smokers, right? But in a case control study, I'm going to get some cases and controls. I'm going to select some individuals who've developed or died from lung cancer, and I'm going to have some individuals who did not develop or die from lung cancer. I'm going to set that at the beginning, right? So it says choose 500 people who died of lung cancer and then 500 who did not die of lung cancer, right? Those with the outcome of interest, meaning died of lung cancer, those are called our cases, and these are called our controls, right? And then I'm going to look at the health history of those individuals and see, were they smokers, or did they have some periods where they smoked and then they quit smoking for a period of time before they died of lung cancer, all right, or not died of lung cancer, okay? So notice here, if I let my row variable be lung cancer and no lung cancer, and this be smoker and former smoker, my fixed totals are my row totals, right? So that 500 there and that 500, those values are fixed, are predetermined at the beginning of our study, all right? Now, if I wanted to calculate P1 hat, right, that would be related to the probability of getting lung cancer given that you are a smoker. Right? But in this case here, all right, I don't have the total here. It would be 273, right, divided by this total of 273 and 173, right? That total there. But I don't want to estimate that, all right? And the reason for that, anytime we have proportions that we're calculating, that numerator needs to be free to be estimated, right? And what we did at the beginning of our study is we set the number of people with lung cancers at 500, or number of people who died from lung cancer at 500. So this 273, which will be the numerator of P1 hat, isn't fully free to be estimated, all right? It's kind of constrained by being predetermined by that total 500 there. The same thing would happen with P2 hat. If I were to try to find P2 hat, I will want this 227 divided by the total for this column here. Again, that 227 is constrained by being fixed by that 500 there. So both P1 hat and P2 hat are not, or I'm going to say should not be calculated because their numerators aren't free to be fully estimated. All right. If I wanted to do this study and still use, let's say, a relative risk, I would have to use my row-wise proportions. All right. The denominator of these fractions basically can be predetermined, but if my numerators are from a predetermined number or a fixed number, I'm not going to be able to truly estimate that. There's some constraints in the way. All right, so I'm going through this example here because depending on how we create our tables, we've constructed the tables the same way in each of our examples. So sometimes your row-wise or your column-wise variables or proportions cannot be estimatable, right? They're not estimatable. So here, column-wise proportions are not estimatable, but row-wise ones are. And in this example, our column-wise proportions are estimatable. But if we were to reorient our table, P1 hat star and P2 hat star are not estimatable. I'm not sure if that's a word. It's probably estimable. All right, but there we go. So to sum this up, it says for certain types of studies, some probabilities cannot be estimated. All right, which means that we shouldn't use relative risk all the time because some of them may not be estimatable. However, your odds ratios can always be estimated because they have the same value no matter if the row-wise proportions, and we're going to say probabilities here, and that's already there. So no matter whether if your row-wise or column-wise probabilities are used. And so since these types of studies are used in medicine a lot, that is why we're going to focus on the odds ratio here. All right, but you still can study relative risks. All right, so that's the end of section 10.9, right? These last two bullets just give us information about some of the advantages and disadvantages of each. For instance, relative risks have the advantage of being easily interpretable compared to odds ratios, right? We're more used to saying probability versus the odds of something happening, right? But, of course, sometimes we can't estimate the relative risk, right? And then the odds ratios have the advantage of being estimatable at no matter what type of study design you have, but they truly are more difficult to interpret. All right, so that really sums up chapter 10 and our study, our introduction to our full study of categorical data analysis. Any questions? Yes.
So how do you find p hat 1 and p hat 2 star?
So P1 hat, good question. So remember, these are now the row-wise probabilities or proportions, right? So if I go here, you notice how I wrote P1 hat as the probability of lung cancer given that you are a smoker. So P1 hat star, I'm going to do it up here in green. That's going to be the probability that you're a smoker given that you have lung cancer, right? And so if I wanted to calculate that, well, I'm going to focus on the row that has the individuals who died of lung cancer, just that row, and calculate. So there's 273 individuals who are smokers and have lung cancer out of the 500 individuals who have lung cancer. And then P2 hat will be the probability that you're a smoker given that you did not die of lung cancer. So I'll look at that second row. I'll do the 173 over the 500. Okay? All right. Any other questions? All right, so what types of variables were all of the studies, or all of the problems in chapters 9 and 10? What types of variables were in those studies? John? I'm going to give you a hint. It starts with the letter C. Categorical, right? When we have one categorical variable, binomial test, chi-square goodness of fit, right? Two categorical variables, chi-square test of independence, Fisher's exact test, and odds ratio, right? So this it gets very difficult. So the next example is, I want to say it's harder than the other, but it can get difficult. But I'll try to make sure that you know what test to use each time on your exam. All right, the very last chapter of this course is chapter 12, right? And so we're switching gears completely. Okay? This is about regression and correlation. How many of you have studied regression and correlation before? How many of you have taken a statistics course before? Okay, so if you've taken a statistics course before, you've done regression and correlation. And we're not going to do much more in addition to what you probably already saw in this chapter here. We'll add some features so that if you get out of the class and you want to do a study, you'll be able to analyze the data, but it's not as difficult as some of the other content. All right, with regression and correlation, we're going to start with this example here in section 12.2. In this study, we have a free living population of a certain species of snakes. That's the species there. The researchers caught and measured 9 adult females. They specifically measured the body lengths and weights as shown in the table here. All right. So notice we have length in that first column is given by X, and then we have the weight of those snakes given in the second column. The weight is in grams. The length is in centimeters. And then we have the mean and the standard deviations, right? Length and weight are the 2 variables in this study. What types of variables are they? Huh?
Quantitative?
Quantitative, you can use the word numerical, right? So part A here says what type of variables and data are given in this study, right? So both length and weight are quantitative. You can use the word numerical variables, right? There's another word that I want to, another description, right, that I want to use when it says what type of variables and data are given in the study. Notice, we've seen data sets that look something like this before. When we looked at the mean difference. Y'all remember that? Mu sub D, y'all remember that? H naught mu sub D equals 0, right? And we did that when we had dependent samples where we used the paired samples t-test. And we had the sign test. But the difference here, so we do have paired data here, which gets confusing, I know. We have paired data because each snake is measured on 2 measurements, right? The length and the weight. But before, when we had paired data, we did a subtraction of the 2 measurements, right? That's how we got mu sub D, the difference. Do you think we're going to do the subtraction of the 2 measurements in this case? Because if we do, then all we have to do is apply what we did before in chapter 8 when we did paired data, dependent samples. What do you think, Jonathan? Are we going to subtract? Yeah? That would be nice because all we would have to do would be apply chapter 8 content, right? Hugh, what do you think? You think no or you? No. Okay. John? Okay, Alexander?
Probably no.
Allie? No. Your team? No. Lydia?
Yes.
Yes, okay. Olivia, I said Lydia, right?
Yeah.
Okay. Olivia?
No.
No, we're not going to subtract. Anila? Molly?
No.
You're going to say no, we're not going to subtract. Grace?
No.
Caroline?